Alright, ladies and gentlemen, welcome back. Today we are going to be looking at section 7.4 and 7.5 in your book. A little bit of each chapter over proportional reasoning. That is, taking something small and extrapolating information to try to figure out what you can say about a bigger version of something. The first thing that we're going to look at here today is called the two-transversal proportionality theorem, or corollary. The two-transversal proportionality theorem says that if we have three parallel lines, like we do here, A, B, C, D, and E, F are three parallel lines, and two transversals cutting them. For example, this line right here, A to E, and this line right here, B over to F. Three parallel lines, two transversals cutting them. Then the segments that are made, like AC and BD, are going to be proportional to C to E and F over to D. We can go ahead and write a proportion just like we've been doing in the past as a fraction set equal to each other. AC over CE, so AC distance over CE distance, is going to be equal to BD over DF distance. We can use this theorem in a lot of different ways. First of all, if we have a triangle, imagine for a moment that we had an extra parallel line sitting over here. Extra parallel line. We have 1, 2, 3 parallel lines, two transversals, A to B and A to C, cutting them. We can go ahead and make a proportion with these segments, saying that this first segment over the second segment is equal to this third segment over this fourth segment. Alright? We can set up a proportion relating all of these segments together. Bx over xa, I'll write this out in red. Bx over xa is going to be equal to, in blue I'll write this next bit, cy over ya. If we plug in values here, and by the way, our goal here is to find cy. That's our job. We're going to find cy. If we plug in our values here, bx is 4, so our equation really is 4 over 9. I'll type that over here instead. 4 over 9 is going to be equal to then 1, 2 for an equal sign. Is going to be equal to the cy value that we don't know over 10, which we do know. As with all proportions, we'll go ahead and solve this by cross-multiplying now. So the 4 times 10, we'll get 40 on one side of our equation. 9 times cy we'll have on the other side. If you now divide both sides by 9, 40 divided by 9, anything divided by 9 repeats over and over again. 40 divided by 9 is going to be 4.4444 and on, and etc. So 4.44 goes on forever, is equal to cy. When you're done with one of these problems, ask yourself, is that a reasonable answer to our problem? If our 9 up here, I'll switch over to green. If our 9 is slightly smaller than 10, then 4 had better be slightly smaller than this bottom side as well. 4 is slightly smaller than 4.4, so it looks like we have a proper proportion. We can use this several different ways. If you've ever had an experience with art, it's particularly doing perspective drawing, you know that in art, if you are going to draw a three-dimensional perspective drawing, there's a vanishing point, what's called a vanishing point. It's essentially a point at which all parallel lines end up vanishing. If we're trying to draw several successive trees, 1 tree, 2 tree, 3 tree, 4 tree right there, and our two trees, first off, are 2.4 centimeters apart from one another. We know that the bases of these trees are 2.6 centimeters away from one another. We know that the tops of the next two trees are 1.4 centimeters, but we don't know how far the bases are apart from one another. We can go ahead and set a proportion with these as well. I'll go ahead and draw out 2.4. I'll choose a better color that's more visible. 2.4 over the 1.4 distance. So I'm going to divide these two sides out. And then I'm going to divide these two bottom sides out, KL and LM. 2.4 over 1.4 is going to be equal to the 2.6 distance over LM. We don't know how big LM is yet. All right. We've set up a proportion. Again, we divided top left by top right, bottom left by bottom right. Make sure you're dividing the same types of things each time. If we multiply these out, we'll go ahead and cross multiply the 1.4 and the 2.6. 1.4 times a 2.6 is a 3.64. On the other side of this equation, we have 2.4 LM. I know that's probably going off the screen a little bit. 2.4 LM. I can do better than that. 3.64 is equal to 2.4 LM. Here we go. Should be more visible in your YouTube video. Dividing both sides now by 2.4. We're going to get a 1.51. Should round to about 1.52 is equal to the LM side. Of course, we need to ask ourselves if this makes sense. Looking up top, 2.4 here. Well, is 2.4 bigger than 2.6? No, it's smaller. 2.4 looks like the top sides are smaller than the bottom sides. The bottom side is bigger, so if we have a 1.4 up top, the bottom side had better be slightly bigger. 1.52 seems reasonable. They're proportional. In the next example, we can go ahead and use proportional relationships. We're jumping into section 7.5 now. We can use proportional relationships when we're taking a small drawing of something, for example, a map of the wonderful state of Wisconsin, and if we're trying relating it to the bigger actual state of Wisconsin. If Kristen, let's say, measures the distance from two cities in Wisconsin to be 11 and 1/8 inch on the map, and we are given that the scale between these two, or the scale on this map, is 1 inch to 13 miles. We can go and set up a proportion then. I'm going to set up a proportion with map in inches over the real in miles. On my proportion, I'm going to go ahead and write down on top 1 inch makes 13 miles. Alright. On the other side of this proportion, 1 inch equals 13 miles, we want to note that 1 and 1/8 inch on your calculator, if you want to figure out what that is in decimal, you can do 11 plus 1 divided by 8. Turns out being 11.125. I'm going to go and type that in as well. In inches, I'm in inches on the map first, on the map, so I'm going to put that on top. In inches, it's 11.125. On the bottom, I don't know how far that is away from how far these two cities are away from each other. So I'm going to leave it as is. If I cross multiply now, 1 and x is just going to make an x. 13 and 11.125. Multiply that out, you're going to get 144.625, I believe, if I'm doing the math in my head right. Of course, the question is asking to the nearest mile. Rounding this to the nearest mile, it looks like these two cities are 145 miles apart from one another. We can also apply this to making scale drawings of things. Suppose you got a sweet new job. You gave up the job from the last lesson of designing Hot Wheels cars, and now you've gotten a sweet job. You're drawing NBA basketball courts. Lucky you. You're going to be drawing an NBA basketball court for a pamphlet. The NBA basketball court, a normal NBA basketball court, has a length of 94 feet. And it has a width of 50 feet. All right. Your job here is going to be to make a miniature version to add to some pamphlet, to some drawing. We're given that the scale is 1/4 inch to 10 feet. That's the information we're given. By the way, 1/4 inch, if we go and put that into decimal, 1/4 inch is 0.25. All right, 0.25 inches for every 10 feet. If we want to set up a proportion here, I'm going to go and set up a proportion of drawing over real. All right, drawing over real. In my proportion, on top, if my drawing is 0.25, this is coming from my scale, my drawing is 0.25 inches, then my real is 10 feet. All right? Now the question is, what do we put on the other side of this equation? It looks like we have a 50, we have a 94, so do we do 50 over 94? No, we don't. If we, let's say, all of a sudden wrote 50 over 94, that would imply that drawing over real is equal to width over length. That doesn't make sense. We need to have the same units on top and the same units on bottom. We're going to need to separate this problem into two separate pieces. So, what we're going to do here, drawing, we don't know how big the drawing needs to be lengthwise. However, we do know that a real basketball court is 94 feet. The real is 94. I'm going to put the real on bottom. After cross-multiplying these, on one side we'll get 10x. On the other side, 0.25 times 94 is a 23.5. Dividing both of those sides by 10, we're going to get that the length of this drawing of a basketball court, 2.35 inches. All right, the length of the drawing of this basketball court is 2.35 inches. We can do the exact same thing now that we've figured out the length. Let's cross out the length. We don't need it anymore. Let's concentrate now on the width of this court. Well, width is 50. Let's get rid of the 94 and replace it with a 50. If we do that and cross-multiply that the exact same way as we did, I'll leave it up to you to do that. We wind up with 1.25 inches for the width, which seems reasonable because our length of our basketball court here, 2.35, should be bigger than the width, 1.25 inches. To check our work, you can think logically here. If we have a 50-foot width, how many 10-feet segments are in 50 feet? Well, there are 5 segments. So if we segment this off into 5 pieces, 5 poorly drawn pieces here, and each of these are 1/4 of an inch. 1/4, 2/4 makes a half, 3/4, 4/4, 5/4 is 1.25 as well. As always, if you have questions, email me. I'd be glad to receive emails from you. Assignment for tonight is the study guide preparing for the Chapter 7 quiz for next time, so be sure to be ready for that. Enjoy. Have a good night.